Hi there, welcome to this lecture on matrix algebra. This is lecture 21, part 1, and the topic today is eigenvalues and eigenvectors. And we will spend 2 lectures on this topic, and this will be the first one. So in this lecture, we will go through definitions and some basic properties on this topic. Okay, let's get started. Now let's begin with considering a linear transformation in the form of a matrix product. So given an n by n matrix, let's call it A, and then we have a linear transformation that's from V to W, where the W is A times V. And let's consider the case where the A is a square matrix of dimension n by n. Therefore, the V will be a vector in Rn, and then W also is a vector in Rn. So we are interested in the image of this linear transformation, and in particular of how they take one vector V and transform it into W, what happens to this transformation. So in the general case, if you just randomly pick any V vector in Rn, then the W would have a different direction from V. It will be turned into pointing in another direction. We can take some simple example. Let's say A is this matrix here, and let's put in the vector V. And then we compute the W, which is A times V, and you carry out this matrix vector product, and you get another vector. And then you see that this vector V and this vector W here, they are pointing in 2 different directions. So here is a graph of them in the x1, x2 coordinate, because this is in 2D, so we can draw it. And the V will be pointing in this direction, 2, 1. And the W is 8, 6, 8, 6, which is the red one. So you see they are different directions. So we are now in particular interested in finding a non-zero vector V such that after this linear transformation, this we call the image W equal to AV is parallel to V. So meaning that if you plot these 2 vectors for the 2-dimensional case, if you have a V and then you compute W equal to AV, it is pointing exactly in the same direction, but possibly with different magnitude. And we see that such a vector is a very special vector for this A matrix, and we are interested in that. Now let's take an example. We have A matrix like this, 3, 2, 1, 4. And let's take a vector V, which is pointing the direction 1, 1. And let's compute the linear transformation, W equaled AV. And if you carry out the multiplication, you will get 5, 5. And then we see that this is just, if you take out 5, it's 5 times the vector 1, 1, which is the vector V. Okay, so we have A times V equal 5 times V. So it's actually predicted in this graph here, this point in the direction 1, 1, and then the W, which is A times V, will point in the same direction, but longer. It's the vector 5, 5. Okay, so such a vector V is, of course, we said a special vector for the matrix A, and therefore we will give it a name. We call this an eigenvector of the matrix A. And then this factor 5 here, that the rescaling of the amplitude of this vector here is also a special number and relating to this eigenvector, so they are called the corresponding eigenvalue. Now we are ready to give a definition. So given an n by n matrix A, so note that it has to be a square matrix, then a non-zero vector So this is important. It has to be non-zero. A non-zero vector v is called an eigenvector of A if there exists a number, lambda, which is the scalar number, such that A times v equals lambda times v. Meaning the linear transformation A times v does not change the direction of the vector. It gets a vector in the same direction, and then lambda is the rescaling of the amplitude. So in this case, we say that lambda is the corresponding eigenvalue of A. So one remark we want to put in here would be that here, if the A matrix, even if the A matrix has all real entries, it is possible that the components of the eigenvector v may be complex, and also the eigenvalue lambda may also be a complex number or even 0. So the eigenvalue can be 0, but the eigenvectors, they are non-zero vectors. So pay attention to that. Okay, let's take a simple example for a 2x2 matrix. This matrix here, and then we see that we can multiply A here with a vector v, which is 1, negative 2. And if we multiply that, and we get 0. And then 0 can be written as 0 times any vector. So it can be 0 times 1, negative 2, which is v. So we have A v equal lambda v, where lambda is 0, and v is this vector. Therefore, v, this vector, is an eigenvector with the corresponding eigenvalue lambda equals 0. And now, in the other hand, if we put in a 0 vector, 0, 0, then A times 0, you get a 0 vector, which can be written as any number times 0. So let's say 1. So we have A times this vector v here equals 1 times this vector v. So can this be an eigenvector? No, it can't, because look at the vector. It's 0, 0. It is a 0 vector. And for a vector to be an eigenvector, it must be non-zero. So this is not an eigenvector, and not 1 is not an eigenvalue. Okay, so here we stress this important fact one more time. That is, an eigenvector must be a non-zero vector. Now let's go through an algorithm to compute the eigenvalue and the eigenvector. So how do we find the eigenvector? Well, we actually find the eigenvalues first, and then we will find the corresponding eigenvectors. So we will use the identity in the definition, that is A v equals lambda v. And we will rewrite it as follows. So lambda v can be written as lambda times identity matrix times v. And then we can move that to the left-hand side of the equation, and then we can take the v out as a common factor. So we'll have A minus lambda times the identity matrix, and then this is a matrix, times v equal 0. So we are interested in the case that this equation here has a non-zero solution, because for v to be a eigenvector, it must be a non-zero vector. Okay. And then we see that if this A matrix is invertible, then we can solve this equation, and you will have a one and one only solution. So only solution would be 0, because if you put 0, it's a solution, and if it's invertible, that's the only solution. And then that is not the case we are interested in, because we want to find out some v that is non-zero. So such a solution where everything 0 is usually called, in these mathematical settings, we call them the trivial solution, which is not what we are interested in. Okay, so in what situation can this equation here admit a non-zero solution V for some choices of lambda. Well, we see that we call this eigenvalue problem, EP. So for the eigenvalue problem to have a non-zero solution, and it is only possible when, for the case where this matrix here is not invertible. And then when is A minus lambda I not invertible? So we know that one property for a matrix to be not invertible is that the determinant of that matrix is 0. So we actually have if and only if the determinant is 0, then this matrix is not invertible. Those two are equivalent. So we have this. So that's why you see we spend so much time talking about determinant. It is very important. So to find this out, determinant of A minus lambda I equals 0, it will lead in the end to an equation, that algebraic equation that involves lambda as the unknown. And that gives us an algorithm to find eigenvalues first, and then we can find the corresponding eigenvectors of A using this equation once the lambda is found. Okay, let's go through the steps. Step 1, we want to find lambda. It might be real or it might be a complex number. And this satisfies this equation, determinant of A minus lambda I equals 0. And in the end, this determinant becomes a polynomial. So we call this P of lambda to denote that expression. And what is A minus lambda I? Well, it is the A matrix minus the identity matrix multiplied by lambda, which means all the diagonals would be lambda. And you subtract these two matrices and you will get a matrix. You can copy the A matrix here and then go through the diagonal and subtract lambda on all the diagonal entries. So we will know that if A is an n by n matrix, then this determinant of A minus lambda I will in the end give you a polynomial of degree n in lambda. And this polynomial is called the characteristic polynomial of A. So our goal here would be to find roots of this characteristic polynomial, which is of degree n. So how many of such roots there are? Well, we can go back and use the fundamental theory of algebra, which says that this polynomial will have n roots. They might not be distinct, and then we write them lambda 1, lambda 2, all the way to lambda n, and they are in C, so they could be complex numbers. And these lambdas would be called the eigenvalues of A. Okay, so we completed step 1, we found the eigenvalues, and now step 2 is to find the eigenvector. So for each eigenvalue, lambda k, we'll have to find the corresponding eigenvector by solving the system, that is A minus lambda k times x equals 0. And we want to find a non-zero solution for that. And we see that this is a system of n equations of n unknowns, because this is a square matrix. And then since the coefficient matrix here have determinant equals 0, then we know that the rank of this matrix is strictly less than n. And then the solution, the system here, would admit a non-zero solution. Let's call it Vk. And then this solution Vk is an eigenvector of A, corresponding to the eigenvalues. So an eigenvalue and a eigenvector, they are kind of a pair that you have to connect these two together. Okay, let's take an example. for 2 by 2, because you can visualize that it's a quite lengthy computation to find eigenvalues and eigenvectors. Let's do it for 2 by 2 just to get the ideas clear. So we have a matrix, and we want to compute first the characteristic polynomial p of lambda by computing the determinant of a minus lambda I, which is the determinant of, put this A matrix here, and then subtract the diagonal with lambda on each. Okay, and then this determinant will be the product of these two diagonal minus those two diagonal. So this minus that. And one can open this up and then combine like terms and write out as a polynomial of degree 2 in lambda. And that's what we will get. To find the roots of this second degree polynomial, you can use your favorite method. You can use the formula, the quadratic formula. Lambda would be, if it's a and that's b and that's c, it will be negative b plus minus square root of a square minus 4ac over 2a, right? So put that numbers in and you get that. And then this one is 49, which takes square root is 7, so you get that. And then there are two solutions. One is with the plus sign and one is the minus sign. Okay, so if you put in the minus sign, you get 6 over 2, which is 3. We call that lambda 1. And with the plus sign, you get 20 over 2, which is 10. So we have two eigenvalues we found. Lambda 1 is 3, lambda 2 is 10. So we completed step 1. And next, we want to find the eigenvectors. Let's start with eigenvalue lambda 1, which is 3. We want to find v1, which is the corresponding eigenvector. And we know that, let's repeat the a minus lambda I on the top here, because we'll use that. So we will put in lambda equals 3 in here and solve this system. A minus lambda I times x equals 0. Okay, put in that lambda 1 value, we get this system here. And we see that these two equations the system gives us are actually the same. So you will have 4x1 plus 4x2 is 0, 3x1 plus 3x2 is 0. Those two are equivalent equations. Basically, you just have x1 plus x2 is 0. Okay, so there's an arbitrary constant here. If you put one of them to be c, and then the other one will be negative c. So you can write out the general solution would be c times negative 1 and 1. And c is an arbitrary constant. Okay, so we see that now we have found the eigenvector. We call this one v1 here, is an eigenvector of A with the corresponding eigenvalue lambda 1 is 3. Now let's find the v2, and we carry out pretty much a similar procedure, but putting lambda 2 equal 10 into the calculation. And then the system you set up is like this. Negative 3, 4, 3, negative 4, x1. So again, we see that the determinant of this is 0 because multiplied by first row by negative 1 is exactly the second row. So you basically have the relation that 3x1 equal 4x2. Okay, so then we can have the general solution for this system would be 4 and 3 and multiply by c, which is an arbitrary constant. So we see that this could be the eigenvector for this lambda 2. Okay, so we now conclude that this v2 here is an eigenvector of A with corresponding eigenvalue lambda 2 equal 10. So this is the end of this part of the lecture, and in the next one we will look into more basic properties of eigenvalues and eigenvectors. Okay, so I hope you enjoyed this, and I'll see you in a bit.